If you looked outside last night, you saw a nice full moon, and I brought a picture of a nice full moon in here with me. This is through a good telescope, I think, because the detail is pretty darn good. But so last night it looked kind of like this. Other times you might see it looks just a sliver of light on it. And I went around and found a few really cool pictures. There's some nice montages people have made of the different phases of the moon, they call it. And what's going on is you basically have the moon going around the Earth, and that whole system is going around the sun. And it's different amounts of light that we can see from where we're at. I mean, the moon is always half lit from the sun, unless it's in an eclipse. But the question is, from where you are standing on the planet, how much of that light are you actually seeing? So there's some nice collections here, but here's one that has all of the different phases of the moon going through time. So you can kind of get a sense of the different kinds of things you'll see. So what I want to ask you about today is how much of the light are you going to see and what kind of patterns are there for that? And in fact, you can look it up. They've been tracking the moon for quite a while now, and they know that it's about 29.5 days for it to complete its whole cycle. But I'll show you some particulars in a second. If you're feeling really inspired, you can I found this picture. This is someone made the phases of the moon out of Oreo cookies. So there you go. They even labeled them for you. New moon, full moon. Makes one hungry, doesn't it? All right, well, here is an animation of the different phases of the moon, and this will let you see kind of what happens. This is over time lapse, so this would be almost a full month there that you're seeing. So I actually looked up a calendar for the current month for April. So this is, I mentioned they have this all tracked out in advance. So what we have next, this is what's going on for this month. And today's Wednesday the 4th. So you see a nice full moon here, Wednesday the 4th. The fullest moon was yesterday. But you see it slowly declines, and then you start getting less and less light on your moon until it's, if you look about halfway down that picture, it's pretty empty. And then if you go a little farther, it goes back and fills up again to the full cycle. So April's kind of nice because you start with a full moon pretty much, and we go through a full cycle. And actually I found there's a naval observatory in Washington, D.C., and they publish what exact percentage of the moon's light you're going to see each night, well, at least from Washington, D.C. They do this at midnight every night. So they have this published in advance for 2007. And I have this list here, and yes, this is kind of small print. What I want you to look at is April right here. We're going to look at all these percentages, and you see that, well, you probably can't see the last two were 100% the last two nights. So what I have done is I have put all this data on my calculator, and I'm going to show you, in fact, here's a listing on my calculator of all these percentages. So this is April 1st, 2nd, 3rd, etc., and then I have 98%, 100, 100, 98, etc. And I made a nice graph of this, and I want you to look at the pattern and see if this possibly looks familiar to you. In fact, if you've had any trigonometry, I bet this does look familiar because this is actually linked to a sine graph. So if you have no idea what a sine graph is, that's okay. I'm going to give you an idea of what it is right now. If you are familiar with the sine graph, it will help you even more. And what we're going to try and do is it won't take too long, we're going to design a little equation to fit how the light phases of the moon go. So hey, you can predict when the moon's going to do it forever, as far in the future as you want to. So on my computer, I have a little animation that I found, and this is going to show you how a sine function works. And it's actually linked to a circle, and what I want you to watch is look at the waveform on the right. It's kind of like a nice little up and down wave. And what actually is going on is it's linked to a circle. So the idea is if you went around a circle and you took sort of a chart of your height, you would end up creating this waveform. So try and think about it this way. Let's say your friend is, I don't know, he's on a Ferris wheel on the circle, and you have a graph on the right, and you're graphing his height, but not in a circular way, but as just moving to the right. So almost like if you were, let's say, walking to the right, but your height was matching the height on the Ferris wheel, you get this nice little wave. So that's where a sine graph comes from. And then I have a sine graph here with some modifications in it. What I want to show you here was you can actually stretch the sine wave however you like. So I have 4 little controls in here. I have an A, B, C, and D. And those are the various places in a sine equation that you could see some extra numbers. And so real quick, I'll show you what they do. That number A out front, if I move it, you can look at the graph there. It's just stretching it up and down. So you can make the wave taller or shorter, whatever you like. The next number you see in there is controlling how wide the wavelengths are, so how long it does to do one cycle. And again, you can make these as narrow or as wide as you would like. Third number in there you see is C. That controls the left and right placement of the wave, so you can actually move it around. And finally, the last one at the end controls the up and down placement of it. So by controlling these, you can have complete control over what the wave looks like if it follows this kind of pattern. So what I thought we could do is we're going to go back in my calculator, and I designed a sine graph to perfectly fit these, this moonlight picture you saw, all these little points. So back to my calculator for a second. Here's an equation. I want to show you why I have these numbers in here that I do. The 50 that we start off with, that's how you stretch the height. So what I've done is I've stretched the height to 50 because that goes 50 up and 50 down, and that makes a span of 100, and that's the percentages we're looking at. We want a full 100% span. Next you see this weird 2 pi over 29.5. Well, that's because the original sine wave has a length of 2 pi, and I want to have 29.5 length, which is how many days it takes for the moon to go through its full cycle. So by putting that special fraction there, I basically made the length 29.5. The 5.1 you see here, I scooted it over a little bit to make it match up. And finally, the plus 50, I moved it up off the x-axis so that it starts on the ground and goes up to a height of 100. And if you look at this graph, what you're going to see is it should fit my points pretty well. So let me turn that on. We'll see how well I did. There you go. That looks pretty good. It's not exactly perfect, but it's pretty close to what that sign, or what the lights of the moon are doing. I'm going to zoom out just a little bit so you can see maybe more in the future that the moon's just going to keep going up and down forever and ever and ever. So a little picture of what the moon does perhaps at night. And what you might find interesting is if you just ask somebody, you know, what would the light of the moon be doing as far as its intensity or how much of it you can see, they might say, well, you know, probably just goes straight up and straight down like a little zigzag, and it actually doesn't. It's this nice sort of smooth curve. You might not realize it's actually linked to the height of a circle, and many, many other things are. For example, I found another example off the moon that we don't even have time to talk about today, but this is a graph of the altitude that you can view the moon at over time. This is for the month of June, and again, look at the shape there. It's very similar to the shape we just saw, and I would bet quite a bit of money that that's actually based on a sine graph as well. And many, many other things are as well. And in fact, if we have time in the future, I'd like to show you some other things. But for example, all the light waves, sound waves, microwaves, waves in the ocean, all follow these little sine graphs. If you take a trigonometry class, you'll learn all about them. But for now, for today, I just gave you a little crash version. So now you have a little idea of what goes on with the light on the moon. You can check it out tonight because we still should have about, I don't know, 98% of the light. I am Mathman Dan, and I am standing here with Scott from Caltech. And behind us, this enormous piece of machinery you see is the Hale telescope at the Palomar Observatory. And Scott's going to tell us a little bit about how the telescope works and some of the math involved with the telescope. And first of all, Scott, at first glance, I don't know about most people, but it doesn't look like a normal telescope. I'm expecting a big tube, and you look in the end of it, but no. Maybe you could tell us a little bit about how this is actually working and where the light is going.
Sure.
It's pointed straight up right now, right?
Yeah. So we, as you just said, pointed straight up, and this big structure in the middle is actually what most people would think of as where the tube is, even though we don't have a closed tube.
Yeah.
But when we observe at night, we open up the dome, and light will come down from the sky and reflect off the big 200-inch parabolic mirror.
You said parabolic, so it really is a shape of a parabola?
It really is.
Okay, so
yeah.
If you're in algebra class and you play with parabolas, we have a parabola here, and so the light comes down, hits the parabola, and then it bounces just right.
So that it comes to a focus at the top end of the telescope.
Okay.
And as those light rays come together, that's where we positioned a camera that looks back down at the mirror to take a picture of what's reflected off the surface.
So no one's really looking at this thing live. It's really the camera.
I mean, no one looks through it at all.
Okay.
Right, right. Yeah. So it's a bad way to do research by looking through and saying it looks blue.
This is true.
Yeah. So
Get a little more scientific about it.
We can make measurements of brightness and position and color and all of those sort of things and record them with the imagers that are used, and the observers see them on their computer screen in real time, more or less.
So back in the studio, we'll talk a little bit about how these angles are working for the light rays, and the parabola is an important part of that. You also told me about a laser you guys actually shine out there. You guys are cheating and making your own stars or something?
Yeah, so we'd like to take this telescope and kind of make it like it's in space. But the problem is we have this atmosphere to look through, and that makes stars sort of be distorted and makes them twinkle.
Okay.
And blurs them a little bit. Well, we use a laser as a calibration source. We can shine that up in different parts of the sky and then make the dot, look at the dot that it makes in the glowing sky and use that as a calibration to undo what the atmosphere is doing and give us a sharper view of the universe.
That's pretty clever.
Yeah.
Now another question I had is how do you know how to point the telescope? Because you were telling me you kind of use a coordinate system, and I I imagine this is kind of like, when you're in math class, you learn how to graph and you have your x and y axes, but how do you guys know where to point it? How do you measure the sky, if you will?
Yeah, well, the sky is set up with lines just like latitude and longitude lines on the Earth.
Okay.
And if you think of those lines and just extend them out to the imaginary sphere that's around us, that gives us a coordinate system. And we know where we are on Earth, and if you know the time, then you know where to point the telescope to see what you want to see.
So would it be safe to say, it sounds like you're using angles and you're not using like X and Y per se, but maybe more like polar coordinates or maybe even better like spherical coordinates if you've had calculus class?
Yeah, definitely spherical coordinates, because the whole sky is this big sphere that surrounds us.
Okay.
And that's how it's all used.
So you're talking like angles, how far down you're going to dip the telescope and how far around you're going to point the telescope, which is exactly spherical coordinates. So.
Exactly right, yeah.
All right, so we have a little algebra and calculus in there to show you. So Scott, thanks for showing us how the telescope works. Back in the studio, I'm going to tell you a little bit about how the parabola focuses those rays, how the light rays bounce, and then we'll talk about that coordinate system you mentioned, so you know exactly where to point that telescope. Scott, thanks so much for your time.
Sure
it's a
thing,
very impressive telescope. It really was a lot of fun visiting up there and seeing all the stuff they have. And our friend Scott mentioned several areas of mathematics that get touched on with the telescope, and the laser, well, that was just cool. But I thought we'd show a little bit about the mirror, and maybe we'll save some of that other stuff for another week. But the mirror he mentioned was parabolic, and it really is a perfect parabola shape, and this mirror was quite difficult to make. I brought a few pictures of the mirror with me. In fact, on my laptop here, it doesn't look like the mirror now because the shiny surface is not on there, but that's the glass basic shape of the mirror. It's actually made out of Pyrex in the 40s, which Pyrex was pretty new at the time, and it was quite a bit of trouble to make. In fact, it took them 11 years to polish it just to the perfect shape. In fact, they removed 10,000 pounds of material in that polishing. So here's a guy polishing it back in the 40s. And then they had to truck it, or actually it was train from New York to California, and the train could not go more than 25 miles an hour. So I guess that took a little while to complete. And then it took 3 diesel trucks to push it up Palomar Mountain and finally into its resting place. Here you see a guy, just to give you an idea of the size of it, he's washing the shiny surface off, which they have to do occasionally because they have to recoat it. And then once it does have the aluminum coating back on, you see it here. This is it roughly in place in the observatory. So it doesn't look like a parabola here. It looks kind of flat, but it really is a perfect parabola. And I made a couple animations to show you why the shape is a parabola. Why would a parabola be the perfect shape for this mirror on this humongous telescope? So first of all, let me show you why a parabola is even in the running. Well, you might have learned about parabolas in algebra class, x squared equations, etc. But really, the defining property of the parabola is all in terms of distances. In fact, if you look at my computer here, this red dot here is the focus. That would be where the camera is. And the blue parabola, if you watch that blue dot moving around, the idea is it's always the same distance between the red line below the parabola, called the directrix, and the red focus above the parabola. So if you could highlight every point that satisfies that, that's the same distance away from those two objects, you really would end up with a perfect parabola. So that's how they're formed. What does that have to do with the light rays? Well, if you have a light source at the focus and you bounce a light ray off in any direction, the cool thing about parabolas is they will all bounce off in a parallel path right out of the shape. So for example, I have here a sample light ray, and I'm going to move it around, change the angle, and you can see how it bounces off the blue parabola. It always goes perfectly straight out. So for example, on your car headlights, you have a lamp at the focus, and the light bounces off and shines straight out ahead of you. The telescope is in reverse, so the light rays come in from the sky, they hit the mirror, and they bounce straight to the focus, which is where Scott mentioned the camera is at. And in fact, here's a whole bunch of light rays, and if I move the focus, watch the red focus move, it changes the shape of the parabola, but the light rays continue to be parallel, even though they may get more or less spread out. So this way we know if we make this perfect shape, we'll have our perfect spot for the camera, it'll collect all the light rays and take a nice picture. So it's actually not too hard to work out the equation that we would want to use. In fact, we're going to do one really quick right now. I have my little math cam running, and on here is a picture of a sample equation, and I made up a hypothetical situation. Let's say I wanted a camera 20 feet away from the vertex of my parabola. There's a set equation that tells you exactly how to make this work. So all I have to do is use 1 over 4p times x squared. P is the distance between the focus and the vertex. If you want 20 feet, I just put 20 in for p there, and I get y equals 1 over 80 x squared. That is the 2D parabola shape. If you make a 3D version of that, you will have the perfect mirror for 20-foot camera distance. Making the mirror is tricky. It took, in the 40s, it took them 11 years to do it. So I'm going to leave that to the engineers. I might want to build one. But that's a shape you would need. So it's a lot of fun going to see that, well, you are seeing a parabola to see the telescope. And in fact, if you can't make it up there for a tour, you can check out their website. They have a lot of interesting facts and history there. And it's run by Caltech. So all you need to do is go to Caltech's website, and they have a whole section for the Palomar Observatory. And I just mentioned suggestions by email. Actually, today we had somebody, a viewer, email us a suggestion for a real-world application of mathematics. And not only did he send us the question he had, but he also sent us his way of solving it. So we're going to talk about that, and if afterwards, if you have time, I'll show you another way to tackle the problem. But he was actually looking at how the planets align. You might have heard people say, oh, the planets align just right, and I got a hole-in-one yesterday or something. Well, he really was looking at how the planets align. Specifically, he saw Venus in the sky. And Venus, it's pretty bright. It looks like a bright star. You can actually see it quite often. But he saw it at the same location in the sky 2 different times. I was wondering how often that happened. So we could look at a related problem is how often does Venus and the Earth line up compared to the Sun? And I looked up how fast Venus orbits around the Sun. So actually that's all we need to know. We already know how fast the Earth goes around. We can actually figure it out. But just to show you what I'm talking about, I made a little animation on my computer that I'll show you. A little crude animation. There's the Sun in the middle. And what I have is the red orbit you see is Venus, and the blue one is Earth. And I tried to get the distances about realistic, about what they really would be relative to each other. So right now they're lined up, and I'm going to send them orbiting around at the speeds they should roughly be. And you'll see that Venus goes faster. Venus is ahead. But eventually, Venus will wrap around and catch up, and they actually do line up again about here. Now, it's not in the same location, but they did line up again against the Sun. So what we want to do is figure out how long does it take for this to happen. So I have a little drawing on my math cam here. Sorry, it's a little less perfect than my computer version, but I have my little Sun and Venus going around in red, and then the Earth going around in blue. Now we do know that Venus goes faster, so I have Venus completing one full orbit, and then the Earth is trailing behind it. So the question is, how much farther are these guys going to have to go? How long will we have to wait until they line up again? And so I'm following our viewer's suggestion on how to solve this little problem. So what I want you to imagine is I've sent Venus around one orbit, and then we have Earth. It's ahead of it, of course. It doesn't complete a full orbit, though, because Venus goes faster. But then I want them to continue, and at some point they should line up again. So this is going to be perfectly to scale, but this will give you the idea of what I'm looking at. So Venus will continue on its second orbit at the same time that the Earth is still moving, a little slower pace, but eventually they should line up again. So the question is, how long will that take? Well, what we could do is we could go ahead and call the amount of the orbit that the Earth completed x. So x here, it's like a percentage or a portion of an orbit. It's not an actual distance. And then Venus has done one orbit plus an additional amount x until they line up again. And I don't know how much x is going to be. It could even be more than an orbit or part of an orbit. But either way, it'll still work out. Just remember that x is some portion of an orbit. So what I want to do is have a look at how these orbits compare. And for Venus, I did one orbit plus an additional amount x, some portion of an orbit. And I want to compare that to the Earth, and the Earth's going to do an x portion of an orbit. And I want to know when those line up again. But the key here is we're not just going to, you can't just set these equal to each other. These are counting orbits, and we need to know when they line up at the same time. So we really need to look at time. And since I know how fast these two guys orbit around our Sun, that'll be no problem. So if we want to look at time, I actually looked up how fast Venus goes. So I'm going to put 1 plus x. This is how many orbits Venus does. And I'm going to multiply by a rate, the rate at which Venus travels, to convert it into years rather than talking about orbits. So I looked it up. Venus does one orbit in 0.615 years. I mentioned it was a little faster than our trusty Earth here. And Earth is easy. We know that does one orbit every year. So I have x orbits on the Earth, and I'm going to multiply it by 1 year per orbit. So this actually gives us a little equation to solve, and the algebra is not too bad. So let's go ahead and solve that guy. So I have 1 plus x times 0.615 equals x. And remember, our units now are years. I'm actually playing with time. So I'm going to quickly solve this, and this is actually going to tell us how long we're going to have to wait for this to happen each time. I'm going to distribute the 615, the 0.615. let's go ahead and take off 0.615x from each side. Here's what I am left with. I have, on the left I have 0.615, on the right I have 0.385x. So, we're just doing some standard algebra. I know not the nicest numbers in the world, but divide both sides by 0.385, and we will actually have our answer. And I did this on a calculator, so what we end up with, it comes out to be about 1.597. So what that would mean for us, this is years, about every 1.6 years, Venus and the Earth should align along a path to the Sun. And it turns out that our viewer commented that he actually observed this similar appearance of Venus about 3 years apart. So that would make sense. It sounds like he skipped one cycle, but he saw 2 of these alignment periods, and that would be about 3.2 years that he witnessed the same phenomenon in the sky. So there's another way you could look at this if you want. This is the way our viewer suggested, and I actually like his method quite a bit. Another way is you could actually look at the angular speeds of the 2 planets. And this would work for anything in a similar situation. For instance, you could look at the clock hands on a clock, and see when they land on top of each other. Or you could look at a car race where 2 cars are going around a track and one's faster than the other. And if one were, for instance, to completely lap the other car, if you knew their steady speed, you could figure out how long it would take for the other car to lap and line up with it again. But we can use our planets here as an example. So what I want to look at is we'll look at the angular speed for each one. And you might have actually seen this in a math class. They talk about angular speed, especially in a geometry or trigonometry class. So we'll look at the angular speeds for each one. Now the Earth is easy, and I'm just going to measure these in orbits. I won't bother with degrees or radians or anything. We'll just talk about orbits. So for the Earth, it's 1 orbit per year, and the standard notation for angular speed, however this evolved, is the Greek letter omega. It looks kind of like a W. It's kind of like a roundy W. All right, so I'll subscript this E for Earth. This is 1 orbit per year. That's its speed, if you will, at which it goes around our sun. And for Venus, well, we have something for that too, because I already know that Venus does 1 orbit, not in 1 year, of course, but in 0.615 years. So we can actually make a rate out of this. I'm going to go ahead and divide that out, and it comes out to be about 1.626 orbits per year. So that's your speed of which Venus is going to orbit around our sun. Well, if you think about what we're trying to do here, we want to know when the 2 orbits align. So we want to know, after a certain amount of time, let's say t years, we could look at how far each one has gone, and we want to know when they're going to land in the same place. So the Earth has gone omega times t, so this is the speed times the time, orbits. What about Venus? Well, Venus has done omega v times t orbits, and we want to know when these 2 guys line up. So I want to know, hey, when are these going to land in the same place? But the thing is, the number of orbits is not going to be the same. It's going to be, Venus is going to have some extra ones because it's going faster. So when they align, what's really going to be happening is we'll have the number of orbits that Venus went, it'll equal the number of orbits Earth went plus some extra ones. That's when they're going to line up. I don't know how many extra ones, but I know that you're going to need some extra revolutions of Earth beyond what the Earth would normally count to match up to Venus, because Venus is going faster. So all I have to know is that k is some integer. It could be 1, 2, 3, 4, 5, I don't know. But this is all we need to know actually to figure out a relationship on how frequently this could happen. So we're going to do a little simple formula here, and I'm going to figure out exactly how often this is going to occur. So what I'm going to do is I'm going to rearrange this a little bit. I put the 2 speeds on the left-hand side there. I'm going to factor out t. So I'll show what the logic is here. And then I just want to simply solve for t, and that'll tell me that if I put in these values, which we know, I'm going to have a relationship here that will show me exactly how much time it takes for the planets to line up. And I know you can get your hole in one or whatever you're working on, right? Okay, so here we go. I have these values. We'll put them in. WV, we already figured out, was about 1.626. Omega of Earth is 1 orbit per year. So really what this boils down to is this value k, which is any integer you want, over 0.626. And if you just do a little division there, it comes out to be about 1.597 k. So what does that say for us? Well, remember, k can be any integer, 0, 1, 2, 3, 4, 5. So what this says is every 1.6 years, roughly, you're going to get the orbits lining up again. And this would work for anything. You can do this with other planets if you look at how fast they orbit, or as I mentioned, you can do it with cars going around a track, or the minute and the second hand on a clock, or anything like that. All right, so next time you're gazing out at the sky, you'll know how often Venus is going to show up like that, right? And if you are a stargazer, if you look at Venus, I have a couple interesting bits of trivia for you. For example, we already know how fast Venus goes around, but Venus is almost as big as the Earth. In fact, I'll show you a picture if you like. This will show you a comparison. Its radius is 95% of the Earth's. However, I don't think you want to visit because it gets to be 900 degrees at Venus. A little global warming going on. One interesting other little tidbit for Venus. One day on Venus, now when I say a day, I mean like, if you wake up at sunrise and you wait till the next sunrise, it's over 100 of our days. So it kind of rotates slowly. I mean, it goes on its own axis, so it's kind of has long days, like living in Alaska or something.